All right, we're going to go ahead and get started. Hi, and welcome to the second in our series of webinars hosted by ANS that feature the winners from the Innovation in Nuclear Energy Research and Development Student Competition. I'm Tyler Newitt from the Innovative Nuclear Research Integration Office, and I will be serving as the moderator for today's event. Before we get started, just a few housekeeping notes. If you have any questions, there is a Q&A function built into the Zoom call. I'll be reading those questions out as they come in after the presentations. So if you have any questions during the presentation, type them in that Q&A box, and I will get them out to the presenters. The event today is being recorded, and there will be a link after the event is over for the recording to be emailed to the event registrants later today. There are also certificates of attendance for the event that are available by request, and you can see the chat for contact information on that. And finally, we ask that all participants adhere to the ANS Code of Ethics and Respectful Behavior Policy, which can be found at ans.org. So with that out of the way, I'm going to go ahead and introduce the first of our presenters today, and that is Jonathan Crozier. John, you can go ahead and introduce yourself.
All right, great. Hello, everybody. I'm John Crozier. I'm a PhD candidate at North Carolina State University, working in the Low Energy Interaction Physics group, and I'm really glad to be here. It's an honor to present, and I'm really happy to be able to share some of what we're doing at NC State, particularly with nuclear data. And with that, let me share my screen and we'll jump in. All right, so I'll be talking specifically about the thermal scattering law for structure-dependent Doppler broadening in flash. And this is a new nuclear data capability. First off, let's just talk about what is thermal scattering and what is the thermal scattering law in the first place. I know for reactor physics practitioners, the thermal scattering law is data that you bring into your calculations, particularly if there's a thermal spectrum scenario. But for a neutron, when the neutron's energy in the thermal range approaches elementary lattice oscillations or phonons, inelastic scattering from phonons can occur. And as the de Broglie wavelength of a neutron also approaches the thermal region, the de Broglie wavelength approaches the order of interatomic spacing, along which elastic Bragg scattering can occur along crystalline directions of high symmetry. So in the Van Hove picture, the thermal scattering law, or S K omega, K being momentum, omega being energy transfer. This is a description of essentially inverse space and what neutrons see. So we see space and time, and we see crystallographic orientations. However, what neutrons and particles see as they're propagating through material is they see momentum and energy transfers. And so the inverse space, the reciprocal description of space and time is momentum and energy. And so essentially this Van Hove transformation is the Fourier transform of a paired distribution function G, which ends up describing in a very helpful way to reactor physics practitioners these low energy transfer states that are now available to thermal neutrons, whereby they can both change momentum and energy. And so an accurate detailing of this is important for reactor physics because it changes the neutron spectrum. And as we're going to see, it doesn't just change the cross sections in the thermal region, but it can also impact in a material-dependent structure way the cross sections in the low-lying resonance range. So in a nutshell, what is thermal scattering law in a little more, digestible terms? What we're talking about is a first principles description of interatomic they actually don't have to be crystalline forces. It's a reciprocal space representation of space and time, and it's proportional to the double differential thermal scattering cross-section. And in this work, the most helpful way of thinking about the thermal scattering law is a probability distribution function for state changes available to a particle. But fundamentally, it is a material property, so it's describing what's available. Specifically, it's describing a specific material. And so here I'm showing the cross sections for the U-235 and plutonium-239, these fissile isotopes, and overlaid with a thermal spectrum from the HTR Proteus. And so this is a room temperature graphite moderated UO2 fueled PBR. And the reason I'm showing you this, overlaid within the context of NDEF free atom cross sections, is that you can see the low-lying thermal energy peak, which is around 0.06 eV, is in pretty close proximity to low-lying resonances. I'm showing this because you can see there's in the black, it's the U-238 NDEF8 total free atom cross section with the uranium and uranium carbide evaluated thermal scattering contribution. So you can see the impact that the thermal scattering law has on the cross sections in the thermal range. So this is specifically showing you the impact of the thermal scattering law on thermal cross sections. But you can see on that slightly higher at the very end of the thermal spectrum, around 5 eV, and just beyond it, you can see the low-lying U-238 N-gamma resonance. It's very large in U-238. And this peak right here is what we're going to be studying specifically for the U-238 resonance absorption in the context of 3 different crystal structures, which have been evaluated with first principles. And we'll be doing that with uranium carbide, uranium nitride, and also uranium dioxide. And so to just briefly describe the motivation for doing this, we know that the TSL impacts neutron thermalization. And very normally, the thermal scattering law is used to evaluate, or is evaluated for generating thermal cross sections, which are very helpful in reactor physics calculations, and also criticality safety as well. Something that's new is that the thermal scattering law informs Doppler broadening and impacts epithermal neutron capture. This is what we're looking at. And so in here, we're going to be generating first principles epithermal Doppler broadened resonance absorption cross sections, which can be imported into a reactor physics calculation, and it's streamlined to go. And this is going to be for uranium and uranium carbide, uranium dioxide, and uranium nitride. So first, the reason we're picking U-238 is just for the low-lying resonance is closest to the thermal region, so the thermal scattering law has the largest impact. And also the U-238 is the dominant isotope, and so it's the largest fraction of uranium in the crystal structure. And here I'm just showing that the N-gamma contribution for the resonance is the largest contribution to the free atom cross-section for U-238. So a little bit of Doppler broadening theory. The gist of it is that essentially Doppler broadening takes one frame of reference, translates it to another, and essentially broadens resonance parameters, which have been evaluated in NDEF, with respect to a distribution of target nuclei. And so traditionally, with the free gas approach, a Maxwell-Boltzmann distribution is used to broaden resonance parameters, which are which are in NDEF and experimental. But in this work, in the low energy region, as we know from normal thermal scattering cross sections in theory, is that the free gas approach doesn't really work when particles approach the low energy region and as their wavelengths get longer. And so the thermal scattering law is a material specific, crystal structure specific approach to describing what the atoms in a crystal structure are doing. And so you can actually use the thermal scattering law to broaden cross sections. And so generally what we do with TSLs is you can have a DFT approach or an MD approach, if anyone's familiar with some of these techniques. And what happens is that with the first principles approach, the game is, or the point is to essentially produce a very high fidelity, accurate description of the phonons in the crystal structure. And so we use DFT and MD to produce a phonon distribution or a density of states. And then that essentially is the kernel and the nugget of the fundamental physics, which we can use in Flash. And Flash is the code that our research team at NC State, the LEAP group, this is a Flash, this is a LEAP code that has been in the development for a good while, and it's an excellent piece of work because it streamlines evaluating nuclear data, and it makes it very accessible and also easy to run thermal scattering law evaluations and then double check that the integral quantities of the thermal scattering law are correct, such as cross sections, all of which can be put into ACE files for whatever kind of calculation you're doing. So all of this work has been done within the context of Flash. So the Doppler broadening has been brought under the wing of Flash. And so both the free gas and the thermal scattering broadening have been essentially they've been made new capabilities for Flash. And so with this, the capability to broaden with the thermal scattering law is now a new feature in Flash. And we'll show some of the data for that. So this is what the phonon density of states are for uranium in UO2, UN, and UC. Below, I'm showing the effective temperatures and also the Debye-Waller coefficients. And now with that density of states, you can kind of see features of that density of states in these velocity distribution functions, which are used for broadening. And so these are essentially the asymmetric thermal scattering law, which is calculated on the fly within Flash over the course of broadening for 6.624 eV neutrons, which is right at that U-238 and gamma resonance for a very low temperature, which highlights the impact of the thermal scattering law. So this is what the distribution, the new velocity PDF looks like. And of course, you can see it's featured. Yes, it's not a Maxwell-Boltzmann distribution function because it captures the crystal structure of each respective material. And as you can see, what I'm showing here are the same velocity PDFs as the behavior with increasing temperature approaches what you'd expect with a free gas. So as the temperature goes up, the distribution, the velocity distribution in each material approaches a Maxwell-Boltzmann distribution, which is as you'd expect. However, all this data is with Flash thermal scattering law data. So here I'm showing what the 0 Kelvin data normally looks like, and just that the free gas broadening is preserved in these new Flash modules. So the new physics the new capabilities are added, but also what's originally and very traditionally done is also preserved. And so here you can see this is what the resonance shapes look like for UO2, UN, and UC. And the comparison is being made between the free gas broadened cross sections at the effective temperature versus what the distribution would look like broadening, Doppler broadening with the thermal scattering law. And below each figure, I also show the percent deviations. And so this shift corresponds to a higher beta sampling of phonon peaks on the left side of the asymmetric TSL. And here, there's an even starker difference because the broadening is not being done at the effective temperature. It's just being done at the temperature that you just give it flat out. So this is the free gas Doppler broadened cross sections at the same temperature as the S alpha beta evaluated Doppler broadened cross sections. And then below I have a plot which compares the absolute difference in barns between the various U-238 in each crystal structure.
And Jonathan, you've got about a minute left before we start to get into questions.
Am I all done? Is that it?
You've got about a minute left. So
okay,
go finish it up.
Okay. And so yeah, in summary, this is some new cool physics that's been streamlined in Flash, and shows the impact of using material specific thermal scattering laws to broaden cross sections in Flash. And this is very user flexible. You can choose free gas, S alpha beta broadening, and also it streamlines generating libraries which can be immediately implemented in reactor physics or criticality calculations. Thanks.
All right, sorry for throwing you off there. Okay. Once again, we're using the built-in question and answer function in Zoom. So if you have your questions, we'll give it a minute and see if any come through before we move on to our next presenter. And I'll give you one to start. Just, you say you're finishing up your PhD. Obviously, it's been some time since you actually, received this award. So what have you done in the intervening time? What has been added on to the work you did for this award, and how are you going to carry it on in the future?
That's a great question. So with this, most of what's been done with this work has been just streaming and parallelizing as much as possible the implementation in Flash. So it's fast. There's been some tidying up in bookkeeping with getting the GUI set up in Flash. So you instead of running it like with punching in input cards and making mistakes, instead a novice user can use the GUI to generate these very kind of advanced reactor physics files with just the GUI. And so that's been kind of the work in progress on that front. And then I've been doing a lot of other very exciting PhD research. Oh, I think you're like
I did mute myself. All right, we got a question through. How can we use the following code in our calculations related to reactor physics? Is it mature or is it under development?
It's very mature. I would say the GUI is probably in the most development. The method itself is quite mature. In fact, technically, yeah, the GUI definitely streamlines things, and that's nice. So the GUI is almost done. But yeah, it's pretty ready to go in terms of implementation and using.
Awesome. Just going to give it another minute for any additional questions or follow-up.
Especially, and also to add on to that, the baseline capabilities of Flash in terms of evaluating thermal scattering law data in cross sections is very vetted and quality assured. And that's very mature. this is a new capability. It's pretty solid, but the baseline thermal scattering law evaluation capability is very, very mature.
All right. Not seeing any more questions come through. So just so you know, if you put questions in after we move on, we can get those to the presenters afterwards and get you an answer back. So yes, if you have any additional questions, feel free to pop them in as we go. But for now, thank you very much, Jonathan. Excellent presentation. And congratulations again on your award. We're going to go ahead and move on to our next presenter, and that is Travis Deason. Travis, if you want to introduce yourself.
Hey, thank you for having me. My name is Travis Deason. I am a third-year graduate student at the University of South Carolina, and I'm also a full-time employee at the Savannah River National Lab. So today, if I can share my screen, let's see. I lost it. There we go. Okay. All right. So today I'm going to talk to you about my work in developing waste forms for the Transuranic elements, specifically the Quaternary Neptunium fluorides. So our motivation in this work is, so currently nuclear waste is mostly put into borosilicate glass. That's the most common, or other glass types such as aluminophosphate glass. It can also be put into syn rock, which is just synthetic rock, or saltstone, which is like a cement type waste form. But some issues with glass is that you do have some volatile species within the nuclear waste stream, such as TC99, cesium-137, or iodine. And of course, when you're making glass, that's a high temperature process, so you can lose some of those volatile species. You also have some low solubility species, which can crystallize out of the glass form and create weak points within the glass. Also, another issue is that it is not customizable. You take all of the nuclear waste stream and put it into the glass. So if you have maybe a more specific type of waste stream, maybe you could benefit from different options. So we are part of an EFRC along with 9 other industries. And the goal of this EFRC is to gain some fundamental knowledge needed to improve the current methods of nuclear waste storage. And the reason that gain fundamental knowledge is in italics there is that we need to understand what type of materials we can make with these actinide elements, and we need to understand what kind of structures they can make, what kind of bonds they like to make, what kind of ions they make. And it's this fundamental knowledge that we don't know a lot of because not a lot of research can be done with these actinide materials. Not a lot of labs have access to do this kind of research. So within this center, you can see here it's broken down into what the different people do. We have me would be in the top left part in the framework solids. So I am synthesizing materials. And the other green sections are also synthetic parts of our center. So we have people working on mesoporous materials such as zeolites. We have people doing metal organic frameworks in different parts of our center. And then in the white sections, you have the actual characterization, and we're studying radiation damage effects, and we're studying modeling of these systems. But like I said, my part's more in the top left, synthesizing framework solids. So in the synthesis, in this paper specifically, I was using a mild hydrothermal synthesis. So it's considered mild because it's less than the supercritical point of water. But I take the Neptunium oxide as my starting material. I take a transition metal precursor, whether it's the oxide, fluoride, or nitrate. I take sodium fluoride as my alkali source, and this is done in hydrofluoric acid. So you can see in the picture there, that Teflon liner, I put all the reactants in that, put that inside of the pressure vessel, close it all up, put it in the oven. And then we go up to 200 degrees Celsius for 24 hours before letting it cool down. So this is based off of research done at the University of South Carolina by other grad students. They had already done work on uranium and thorium because USC has permission to do work on those low dose or low activity actinides, and also cerium and plutonium had also been done as well. The plutonium research had been done at SRNL, but then we moved that onto the Neptunium. So with this work, I was able to synthesize 9 different compounds of the Neptunium, and you can see the formulas written right there. In the picture to the right is the titanium version, so Na3Ti NP6 F30, and then just by changing out that transition metal, we were able to come up with those 9 compounds. And you can see here, when we do go to analyze the crystals, in the picture on the right is the microscope setup we have in the hood. Since these are radioactive materials, the whole setup has to be in the hood to look at them. So you can see the computer on the back allows us to view the crystals, and then the whole setup is all contained within the hood. On the left, once we've actually isolated a single crystal that we want to analyze, then we glue it to the end of that mount. And then we also put a thin plastic sheath over the top of that and use epoxy around the bottom of that plastic sheath. And that gives us like a double containment. So it's more secure within that mount. And then we're able to send that to USC for single crystal X-ray diffraction. So during the crystal analysis, we were able to determine that this structure does form a framework structure. It is built from a tricap trigonal prism building block. So that's Neptunium bonded to 9 fluorine atoms to give us that building block. That building block, edges and corner shares to form the framework structure that you see there in the center. And depending on the transition metal that we use, if it is a trivalent transition metal, that trivalent transition metal sits in the largest void created in the framework structure in the center. And then the smaller hexagonal voids on the outside are filled with the sodium. And sorry, also the center void is alternatively filled with transition metal and then sodium atom and then transition metal. That's why you see the yellow dot in the center there. On the right, if it is a divalent transition metal, you need another sodium atom to charge balance the structure. So another sodium atom will fill the space in between the building blocks making up your framework structure. So since we were able to make 9 different structures, we were able to determine the ionic radii of the Neptunium. And this kind of goes back to the base knowledge that we're trying to gain from these structures and from this research. The ionic radii of tetravalent Neptunium was not known or was not reported. And that's kind of basic information that you need to know in order to determine what kind of structures you can make from different atoms. So like I said, each structure is made of Neptunium bonded to 9 fluorines. So I was able to take those non-bond links and average those. You can see that in the chart. And then take the average of those averages. And that's where I get the 2.315 angstroms from. I subtract out the ionic radii for fluorine itself, which is known and reported, to get the ionic radii of the Neptunium. And so we were also able to go back to the previous research done in our group and do the same thing with cerium and plutonium, which had also not been reported before. And we went through the same process with the uranium and thorium that we had made, just to kind of use the same process on the uranium and thorium, which had already been reported, but just to kind of lend confidence to what we were doing and say, hey, these numbers have been reported, but if we do the same methodology that we did with our Neptunium, we do get the same answer. So we were able to report those values. And you can see here when we plot the volume versus the ionic radius cubed, that you do end up with a linear relationship between those two variables. And our correlation factor was, the R squared value is almost 1. So it is a linear relationship. And again, that lends confidence to how we determine the ionic radii, because it's supposed to be a linear relationship. So for the next steps, we hope to extend this out a little bit. You can see in this graph here that the blocks in green are structures that have already been synthesized before, and the ones in blue have not been synthesized. So you can see that thorium is the most built out section there, and that makes sense since it is the largest actinide radius, and so it can accommodate a lot more ions with different sizes. The uranium is the next most filled out section there. The Neptunium is the one this research was focused on, and then it gets less and less as you move on, but you get a smaller ionic radius as well. So maybe it's just not able to incorporate the different size transition metal radii. But we do hope to extend that a little bit. So the plutonium had already been done a little bit before, but it was cut short by COVID, by the grad students that was working on it. So we think more can be synthesized than has been already. So we hope to go through and extend that a little bit. So you can see there, I have synthesized the gallium of the plutonium fluorides, and we think we can do more. So we're going to try to do that as well. Another thing that we did with this research is we took the cerium analog. So instead of the Neptunium, we took the same compound with cerium, and we sent that to the University of Michigan to do a xenon ion beam irradiation to try to determine how well the crystal structure holds up to radiation damage. So they took a selected area of electron diffraction to monitor the amorphization of the samples. So as the xenon ion beam is, pointed at the sample, they can analyze and see how long before the sample is not crystalline anymore. So you can see in these pictures, this was done at room temperature, that at 0 dPa, and that is displacements per atom, that the structure shows that it is crystalline. You get a nice diffraction pattern. And as you increase over time, that diffraction slowly fades. And at 0.041 dPa, it is gone. So the graph at the bottom shows the same thing, just in graphical form versus just seeing the pictures. But again, 0.041 dPa before it is not crystalline anymore, it's amorphous. The 0.041 dPa is a fairly low resistance to amorphization. It does become amorphous fairly quickly. But that is not the only characterization you want to see in a waveform. So you can also look at the thermal stability. Some other reports done on some analogous structures of the thorium version show that they are thermally stable up to 500 and 800 degrees Celsius, which is a very good characteristic for a waveform. It has also been shown to be resistant to nitric acid and even aqua regia. And you can see in these pictures on the bottom here that the crystals of the plutonium analog were shown to be acid resistant as well. So the initial crystals on the left versus after 24 hours in concentrated nitric acid, it is still crystalline. So again, acid resistance and thermal stability are good characteristics of waveforms. Oh, sorry, I thought I had a acknowledgement slide, but anyway, that's the end of my presentation here. I guess I need to thank everyone that I work with at USC and at SRNL. And I'll take any questions you have. Thanks.
Awesome. Thanks, Travis. We'll give it just a moment here for questions to come in. All right. We have alkali cations besides sodium been tried? What is the effect of substituting the sodium for something else?
Yes. So far we've tried potassium and rubidium, but haven't had any luck yet. We also tried cesium, and if you do cesium, you end up with instead of an actinide 6 F30 structure, you get an actinide 3 F16 structure. And so that has been done and reported with uranium and thorium, and we are looking at doing that with neptunium and plutonium as well. So it does change the structure. It's the same building block. It ends up still being a 9 coordinated actinide material, but it does give a different structure.
Any more questions for Travis? All right, not seeing any come through, so we'll go ahead and wrap it up there, Travis. And again, if any of you have any questions for Travis that you didn't get into the chat right away, you can put them in and we'll get them to Travis once this is all done. But thank you once again, and congratulations as well. And we will hand it over to our final presenter today, and that is Kelsey Green. Kelsey, you want to introduce yourself?
Hi. I'll share my screen really quickly and then I will introduce myself. Does this look good, my screen? Hopefully it does.
Yep.
Awesome. Okay. So hi, everyone. My name is Kelsey Green. I actually graduated with my PhD from the University of Michigan back in November, and I am currently a postdoctoral researcher at Los Alamos National Laboratory. But today I'm going to be presenting work that I completed as a graduate student when I was an intern at Oak Ridge National Laboratory. And that is going to be on the effect of shielding gas on composition modification and precipitation in an additively manufactured iron 9 chrome steel. So to begin, why do we even care about advanced nuclear reactors, and specifically the materials that are used to construct them? So advanced nuclear energy is a clean energy option that can provide an abundance of low carbon electricity and is key to achieving sustainable energy systems. And as the IEA said, without nuclear investment, achieving a sustainable energy system will be much harder. So we care about nuclear for its ability to provide a cleaner and greener future. However, advanced reactors' operability and lifetimes are limited by the capabilities of traditional steel alloys that are used to construct the reactor cores. These materials are called structural materials as they house the reactor core and encase the nuclear fuel. These metallic alloys need to operate under harsh environmental factors in order to ensure safe and long-lasting reactor operation without degradation. But the operating conditions are pushing the limits of current materials viability, and thus it's necessary to increase the alloy performance through tailored design. So one key design feature of interest is inducing a high density of stable precipitates. So precipitates are a secondary phase embedded within the steel's matrix. The metallic alloys that are candidate materials for advanced fission reactors are iron-based steels with about 85 to 90% iron, and thus they have a matrix that is mostly composed of iron. And you can liken precipitates in a metal to sugar and water. So once you reach a certain limit of sugar, sugar clusters begin to precipitate out of the water, which is akin to the matrix. So likewise, once a certain concentration of an element, such as vanadium, is reached in the steel matrix, the vanadium atoms will cluster into vanadium-rich precipitates. And these precipitates are desired in the matrix because they have been shown to improve high-temperature mechanical properties and also radiation tolerance in iron-based steels. So alloy designers are interested in increasing the amounts of these precipitates in steels. Traditionally, this has been accomplished through changes in composition and tweaks in the traditional manufacturing process, but you do reach a limit with those kinds of methods. So with the advent of additive manufacturing, also called 3D printing, interest has grown to understand if additive manufacturing can be used to tailor materials specifically for advanced reactors. And my research focused on tailoring precipitation behavior in steel by using additive manufacturing. And the goal of this research was to improve the properties and radiation tolerance of a steel that is a candidate material for advanced reactors through controlled precipitation, and hence to increase the performance and safety and hopefully the lifetime of advanced reactors as well. And the precipitates that we are interested in and that we're going to be talking about are called MX precipitates, where M stands for metal, such as vanadium or niobium, and X stands for carbon and or nitrogen. So these are what are called carbonitride precipitation. So first, my collaborators at Oak Ridge National Laboratory printed 2 bulk specimens. So as you can see, additive manufacturing is a process by which a sample is built up layer by layer. And we used a specific form of additive manufacturing called wire arc additive manufacturing, by which a wire feedstock material composed of iron, chromium, and a small amount of other elements such as niobium and vanadium was fed and then deposited onto the substrate as a welding head welded the wire layer by layer until achieving the desired geometry. And we just did a simple geometry. So the final product is shown in the picture there on the right. And this composition, like I mentioned, the composition of the feedstock material was used because it represents a current leading candidate alloy for advanced fission reactors. So for those of you familiar with materials, it represents grade 91. So the 2 as printed builds were made with the same initial steel metal composition, but they differed in one very important way. And that was that the composition of the gaseous atmosphere that was used during their fabrication. So one specimen had a mixture of argon and 1% nitrogen gas circulating during fabrication, and the other had a mixture of argon and 5% carbon dioxide during fabrication. So for these 2 different builds, I will refer to them as build N2 or build nitrogen and build CO2 or build carbon dioxide for now on for the rest of the presentation. So the point of having these 2 different atmospheres during fabrication is to see if the nitrogen or carbon in the shielding gases affected the resulting MX precipitation. And so generally, if you're interested in a little bit more about additive manufacturing, generally an inert shielding gas such as argon is used to control the stability of the welding process, inclusion content in the steel, as well as the microstructure and resulting mechanical properties. So we also performed 2 different typical heat treatment processes called normalization and tempering, whereby samples were cut from the as printed specimens and they were heated at high temperatures for a set amount of time. And this was in order to remove residual stress that is incurred during the AM process itself, and also to produce equiaxed grains, which is better for isotropic mechanical properties. So we had 6 samples that resulted from this work, 2 as printed and 4 heat treated samples. And they were characterized to ascertain their microstructures as well as their mechanical properties. So we wanted to characterize the precipitates in the sample on the nanometer level, which is not visible to the human eye. So to do this, we used different types of electron microscopy in order to create small samples and then subsequently analyze them. So an example of a composition map that was taken with electron microscopy is shown there on the bottom right. The colors represent different elements, and then the clusters represent precipitates that are enriched in those elements. So these images allowed me to count and measure precipitates in the materials, in the as printed and the heat treated materials, in order to obtain results on precipitate size, amount, and composition, in order to understand if that shielding gas had any effect on the resulting MX precipitation. So the first thing that we checked was if the different shielding gases affected the final composition of the as printed builds. And we found that the nitrogen-rich shielding gas caused the nitrogen content to increase by about 60% in the as printed build over the feedstock material, and that the carbon-rich atmosphere caused about a 16% increase in carbon content. So we were successful in using the shielding gas composition to tailor the carbon and nitrogen content in the resulting additively manufactured builds. But we also wanted to know if this translated into the ability to tailor the MX precipitates. So these results, which again are composition maps, show 3 different kinds of nanoscale precipitation that occurred in the as printed specimens. And these are represented by green, red, and blue arrows in these figures. So green is for vanadium nitride precipitates, red is for niobium carbonitride precipitates, and blue is for vanadium niobium carbonitride precipitates. And importantly, the different precipitates showed up in different amounts based on the gaseous atmosphere that was used during sample fabrication. So for instance, build N2 contained more precipitates enriched in vanadium and nitrogen than build CO2 did. And build CO2 contained more niobium carbonitrides than build N2 did. And this difference in precipitate composition remained true after heat treatment as well. Thus, the shielding gas affected the composition of the resulting precipitation in all specimens. In addition, the as-printed specimens had about an order or two of magnitude greater density of precipitates over the heat-treated specimens, as well as over values given in literature for traditional steels fabricated with traditional processes. So that's a good thing to increase that precipitate density. But an obvious question emerges from these results of why the shielding gas atmosphere affected the composition of the resulting precipitates. So we can take build N2 as an example. So first, the nitrogen particles are added to the gaseous atmosphere during additive manufacturing. And these nitrogen particles are then absorbed into the matrix of the as-printed material during printing. As the material continues to cool after printing, the nitrogen particles will attach to other metallic elements and create clusters or precipitates. And nitrogen has a greater affinity or a greater attraction to vanadium than other elements, therefore making more vanadium nitride precipitates. And this would be in contrast to build CO2, which had a greater amount of carbon content. And carbon has been shown to have a greater affinity or attraction for niobium. So this means that in build CO2, you had more precipitates enriched in niobium and carbon. But even though the different specimens displayed different amounts of compositions of precipitates, both of them did have an increased number of precipitates over steel manufactured with traditional methods. So it seems that the process of additive manufacturing does increase the density of precipitates. Now, what is most important to reactor designers is the properties of a material, such as its strength. So we will now talk about strength to see if these differences in precipitate compositions had any effect on the properties of the materials. So here you can see a plot that shows the strength of the samples on the y-axis versus the test temperature. And the samples were tested at room temperature, 330 Celsius and 550 Celsius. And these higher temperatures are relevant to advanced reactor operations, specifically for like cladding material. And there are three key takeaways from this graph that I'll walk you through. So the first is that the as-printed specimens, which are shown by triangular symbols, had greater strength than the heat-treated specimens, which are shown by circles and squares. And this difference in strength became even more pronounced as temperature increased, whereas the heat-treated samples seemed to lose their strength as temperature increased, but that effect was not as pronounced for the as-printed specimens. Second, the heat-treated specimens had comparable strength to traditional steels that had the same composition, and the AM samples had greater strength than both the heat-treated samples from this work and from those traditional steels from literature. So the stars here represent the literature values of the strength of those traditional steels. And it's hypothesized that the additively manufactured samples, the as-printed samples, have greater strength due to a higher dislocation density, a finer grain structure, and that increased precipitation that we talked about. And third, alterations in the shielding gas composition did not appear to have any detectable effects on the mechanical properties. So basically, the different precipitate compositions did not affect the strength of the materials. What seems to matter more is if you have a greater density of them, but not necessarily the composition. In fact, you can see that for some of the conditions, the samples that were made with different gases and tested at the same conditions actually had overlapping strengths. So in conclusion, this study successfully fabricated an advanced steel with additive manufacturing, which was only the second ever recorded printing of this particular steel. And it proved the ability to control precipitate chemistry with shielding gas composition, which was also not shown before. Thus, these results that connected processing, structure, and properties contributed significant findings for the use of additive manufacturing in the development of materials for advanced reactors, hopefully contributing to increased nuclear energy adoption and hence to a balanced low carbon energy mix worldwide. And finally, if you found this research interesting, you can check out my publication in the Journal of Additive Manufacturing, and also stay tuned for a future publication in which will be discussed the effects of low dose neutron radiation on these samples, which has also not been reported before. So yeah, thank you very much for your time, and I'd be happy to take any questions if you have any.
All right, thank you, Kelsey. We'll give just a minute for questions to come in here. But thank you very much for your presentation. And as we're waiting, I'll ask an intro question along the same lines I asked Sean. you said you're at Los Alamos now?
Mhm.
So how much of your work as a graduate student were you able to carry forward, and what are you working on now?
Yeah, that's a great question. So the research that I presented right now, this was actually not my PhD research. It was a side project for an internship. But I am currently probably going to try to look at the materials that I just talked about with more electron microscopy characterization after they've been neutron irradiated. So hopefully that project gets funded. We can continue this research. And then for my PhD, my work was also on an iron-based steel and just radiation effects, particularly helium effects in that material. And I still currently work on iron-based steel at Los Alamos. So I have two projects based on creep testing, as well as impurity effects in an iron-based steel.
Awesome. We'll just hang on a little bit more. Oh. All right, we got a question. Will you be selling t-shirts that say sugar equals vanadium?
Sure, why not? Let's do it.
Awesome. All right, we'll give it just a couple more minutes here. See if any more questions come in. And again, if you have any questions for our previous presenters, you can feel free to pop those in the chat and we can get answers from them. But I am not seeing any additional questions at this time. So thank you very much, Kelsey. And thank you to all of our presenters today. We really appreciate you taking the time to show off your excellent work here. We at the NAUP office are very excited. We have this year's Innovations in Nuclear Research and Development student competition, which closed earlier this year, and we should be announcing awards on that later in the spring. And if you are interested in entering this competition next year, it'll be open sometime this fall for the next round of applications. So, but we're really excited to continue to have the opportunities to show these students excellent work. I don't have off the top of my head, Cece, do you know when the next one of these is scheduled for?
Yes, I could tell you in just a second.
Sorry to put you on the spot.
No worries. Okay, it looks like it's April 16th.
All right, so we will have the next in our series of the FY23 winners April 16th. And we hope to see you all there. But for now, thank you very much for attending. Thank you to ANS as well for hosting once again. And have an excellent day.